Now, can everybody hear me? I hope yes. Okay, good. We're good to go. Right. Like we were talking yesterday about risk quantification. So let me make this 2 by 2 table. Talk through that. So what we had as an example yesterday was lung cancer, no lung cancer, and smoking present, smoking absent. Like I said, we use odds ratio for We use odds ratio for case control studies, and we use relative risk for cohort studies. Now, let's brush up a little for 5-10 minutes, like what we spoke yesterday. Case control studies go back in time, trying to find out the association of a risk factor with the disease. So what do we have in hand for case control studies? We know that we have the disease, all right? We have those people with lung cancer. We're trying to find out if they were smoking in their history back in time. So that is what we're trying to find out, right? So we have lung cancer. This is the section you already know. This is the section you make up because you want to match for a control group. So you select people with no lung cancer and then go back in time and see if even those people have smoking history or not, right? So this is precisely what we have. We have people with lung cancer, but we want to find out in association with smoking, whether smoking is present in all those people who have lung cancer, so that we can find an association. Okay, all right, if there are so many people with lung cancer who also smoke, so what information is it giving us? It simply says that people who smoke are more likely to develop lung cancer. That is, there are more odds of people to develop lung cancer if they smoke. So the odds of developing lung cancer with smoking will be higher. Okay, so just in case, if you would find out that the odds of developing lung cancer is more among people who do not smoke, what inference do we derive from that? We understand that, okay, it's not smoking that is causing lung cancer, but instead, not smoking is what is causing lung cancer. That is the inference we derive, right? So for odds ratio, it's like, what are the odds of developing lung cancer among people who smoke? Okay, so that will be given by the odds of, this is the people with lung cancer, right? And the people who are smoking as well as having lung cancer is this, by 1 minus the probability. And we derived it, we did the math, and we got A by C yesterday. So A by C is the odds of developing lung cancer among people who smoke. So what are the odds of having no lung cancer in spite of smoking? So we're comparing the people who have lung cancer with the people who do not have lung cancer, and we're taking into consideration smoking as a risk factor, because this is what we're trying to find out, if there has been smoking in their histories. If we find that smoking was there in the history of people with lung cancer, and there was significant amount of people with lung cancer with a smoking history, that simply says that the odds of having smoking as a history in people with lung cancer is higher. So we want to have A by C greater than B by D. In order to say that smoking is associated with lung cancer, definitely A by C, which is the odds of having lung cancer in people who smoke, should be definitely greater than the odds of having no lung cancer among the people who smoke. All right. So if A by C is greater than B by D, okay, what's the odds ratio? The odds ratio is this divided by this, that is A by C divided by B by D. Okay. Yeah, sure, Aditya. I'll tell you ROC curve in the end. We'll talk about it in the end. I just missed it yesterday for you, but not a problem. I'll tell that to you in the end. Okay. So, like I was saying, so the odds ratio is going to be A by C divided by B by C. Odds ratio is not A by C. Odds ratio is not B by B. It's the odds for having lung cancer among people who smoke. This is the odds of having no lung cancer among people who smoke. The odds ratio is you divide this by this. Now you want to have this greater than 1. Tell me why? Because if it is greater than 1, obviously A by C is greater than B by D. And if it's not, then the inverse of what the actual hypothesis was would be true. Our hypothesis is that smoking is associated with lung cancer. So we want to have A by C greater than B by D. Don't simply memorize AD by BC for odds ratio. It's not going to help you anyway. All right. Do remember that this is the odds for smoking and having lung cancer. This is the odds for smoking and not having lung cancer. And the odds ratio will be, if you divide those two, you'll get the odds ratio. Likewise, if you talk about relative risk, now in relative risk, where do you use relative risk? You use it for calculating the risk in a cohort study. So what do we have in cohort study? We know that we want to find out if smoking does cause lung cancer. We want to find we want to prove the causality actually. And we already know that there is an association with lung cancer and smoking. And now we want to prove the causality. What's exactly causing? Is smoking really causing lung cancer? That is what we want to find out. So in cohort study, you take smoking, you take all those people who smoke. So this will be the column with smokers, right? And this will be the column with non-smokers, right? So you take smokers, you also take non-smokers, you follow them forward in time, maybe 10, 15 years down the line, and then you'll evaluate if these people have developed lung cancer. Right? So if they did develop lung cancer, and then we'll have to find out if the development of lung cancer among people who smoke was higher, or the development of lung cancer among people who didn't smoke was higher. If the number of people developing lung cancer are also smokers, okay? So the number of people who were smoking developing lung cancer, if they are on the higher side, we can say that smoking, yes, smoking has caused lung cancer because we don't have lung cancer now. We are only taking people who smoke. We are only taking people who do not smoke. And then we are following forward in time down the line, like 5, 10, 15 years later. And then we are evaluating if they did develop lung cancer. Okay? Any questions so far? From the people online, any questions so far? Okay. So how do we actually formulate this relative risk? So the risk of developing lung cancer among people who smoke. So these are all the people who smoke. All the people who smoke are A plus B. Am I right? So how many people, what is the rate of development of lung cancer among people who smoke? These are the people who develop lung cancer, A, out of all the people who smoke. So the risk of developing lung cancer among those who smoke is this. And the risk of development of lung cancer among people who do not smoke will be this. Now, what is a relative risk? So you're comparing smokers with non-smokers. So when you're comparing smokers with non-smokers, you gotta have A plus B divided by C plus D. So this is the relative risk of developing lung cancer for smokers when compared to that of the non-smokers. Okay? So this is what you've got to remember. All right. Now, if I say that the risk of developing lung cancer when compared to those among smokers, when compared to those who do not smoke, is 10. That is, in simple terms, if the relative risk is 10, what does this imply? So people who smoke are 10 times more likely to develop lung cancer than people who do not smoke. That is the inference that you derive out of, right? So for every 10 people developing lung cancer, there's one person who's developing lung cancer who do not smoke. So if there are 10 people with lung cancer, they smoke. There's one guy who's developing lung cancer who does not smoke. Okay? That is the inference you get out. Now, the next thing, attributable risk. Now, attributable risk, what is this? It is event rate of control of treatment minus event rate of control. Treatment or risk factor. Okay? Event rate of a risk factor or treatment minus subtracted from event rate of control. Okay? So from the same table, A, B, C, D, lung cancer, no lung cancer, smoking, no smoking. Okay. Now, what information is attributable risk giving you? Now, like I said, if the relative risk is 10, now what is the attributable risk? Attributable risk is event rate of risk factor minus the event rate of control. So what is the event rate of a risk factor? How many smokers are developing lung cancer is the event rate of the risk factor? A by A plus C minus what is the event rate of control? This is the group that is under study, smokers. This is the control group, non-smokers. Any confusion? You want me to repeat again? Yeah, sure. So, in cohort study, what I said is, cohort study, all that we have is people who are smokers and people who are not smokers. We don't know if all those people have lung cancer or not, or they do not have lung cancer. All the information that we have is whether they're smokers or not smokers. And then we follow forward in time and we keep track of the history. I mean, how long have they been smoking? For 5 years, have they developed lung cancer? For 10 years, have they developed lung cancer? For 15 years, have they developed lung cancer? That is what we find out, right? So this is our study group, the smokers. We want to find out if smoking is causing lung cancer. So that is our study group. And non-smokers is our control group. Okay? Anything else? No? Right. So attributable risk is given by this formula, but why do we have to find out? Like, what is the significance of this particular thing? The attributable risk, it gives you a number wherein how much is smoking attributed to its causing lung cancer. When we're talking relative risk, we're comparing this with this in the number of times. But how much can smoking be attributed towards causing lung cancer? So, like I said, if the relative risk is 10, what information is assuming? 10 times more likely. So if 10 people are developing lung cancer, there's one guy. So attributable risk is what? So how much is smoking attributing towards causing lung cancer? It's 10 minus 1. So for having one person who has lung cancer who does not smoke, you'll find at least 9 guys who have lung cancer and who smoke. That is attributable. How much is smoking attributing towards causing lung cancer? So it's, I mean, smoking is like you can easily find 9 guys who smoke and have lung cancer compared to one guy who has lung cancer and does not smoke. I'm not able to see the board. Is it visible now? Swapna, is it visible now? Still not able to see?
The board is visible, sir, but the writing part will be audible.
Excuse me?
The writing part, what you're writing on the board.
You want me to move it towards my right hand side?
Yes, sir. The writing part I'm not able to see, sir. Remaining all.
Excuse me?
Writing part I'm not able to see, sir. Remaining all.
I'm not able to see. Okay.
Sir, no audio.
I'm not speaking actually. Can you see it now? Everybody? I didn't speak first.
Okay.
I was Hello?
Okay, sir, better than before, but
Okay. Can you see that? I mean, what all I'm writing on the board? Is that visible to you?
no, sir.
No?
No, sir.
Okay. I'm trying to make arrangements other than that. Excuse me? No, I'll make use of this writing pad maybe. I'll make use of the I'll make use of this writing board. Okay. Will this be comfortable for you if I write on this?
Yes, sir. It is okay.
Excuse me?
Good, sir. It is clearly visible, sir.
Okay, fine. If this is comfortable, we'll deal with this, all right?
Okay, sir.
Okay. Can you hear me all?
Yes, sir.
Right, let's get started. Okay, so everybody can see the board and the presentation as well. Can you? All right. So like I was talking about attributable risk. So attributable risk is given by the formula A by A plus B minus C by C plus D. Okay? Right. Next to that is absolute risk percent. Why don't I get the whiteboard? Okay. So everybody can see and everybody can hear, right? So the next thing is attributable risk percent. If you don't have this formula in first aid, I want you to write this, make a note of it. It's given by the formula relative risk minus 1 divided by relative risk into 100. Okay? So questions on relative risk percent are pretty straightforward. Okay, absolute risk percent, relative risk minus 1 into 100 divided by relative risk into 100. Okay, so that is at absolute risk percent. Okay. Next, number needed to treat, number needed to harm. Number needed to treat, number needed to harm. So basically, if I'd say that the prevalence of diabetes in the population is 10%, like there are 10 people among the 100 people, like there are 10 diabetics among the 100 people that is the population under study. So how many people are you going to treat in order to prevent? You can't prevent diabetes. Maybe pneumonia. If the same thing. If I shift to pneumonia, the prevalence of pneumonia is 10%. So how many people are you going to need to treat so that you won't find a case of pneumonia? So that is what it actually means. Number needed to treat and number needed to harm. Okay, so that's given by the formula. Number needed to treat will be -1 by attributable risk, and number needed to harm will be 1 by attributable risk. Okay. And we'll talk about number needed to treat and number needed to harm more when we do the questions. I have a few questions at the end of the session, so we'll talk about it there. Okay. So here's a question for all of you. The time that you'll be given is 2 minutes to read the question, read through the options, and calculate. Do whatever you want and give me the answer. Because I just want you to, orient yourself to the real exam. Because spending more than 2 minutes of time, you're not going to finish the block. All right. So this is what you need to practice every time. So here you go. Question for today. Okay, I'll just magnify it.
Can you read the question for us?
Sure. A study evaluated the role of ACE inhibitors in the prevention of coronary events in diabetic patients. During 5 years of follow-up, 120 diabetic patients out of 400 who had taken an ACE inhibitor developed an acute coronary event. Over the same time, 100 diabetic patients out of 300 who had not taken an ACE inhibitor experienced coronary event. What is the relative risk of developing a coronary event in diabetic patients taking ACE inhibitors compared to diabetics who are not taking ACE inhibitors? Yeah. You have 1 more minute left. Okay, time up. Everybody got their answer with them? All right, let's have a 2-minute discussion on this question. The point that you all need to know is that this guy, he doesn't want you to solve the question for him. And most of the questions are of this sort. He just wants to evaluate if you know the concept or not. He doesn't want you to solve the questions. The math part, he doesn't like that. He just wants from you guys that if you've noticed like what relative risk is, how to calculate it. From the question, it said that there are 120 guys out of 400 guys, okay, who had taken an ACE inhibitor and who has developed an acute coronary event. So the top portion, I mean, this column, here you have acute coronary event. Okay? This is the disease, coronary event. And here you have, no. Okay, so acute coronary event, no coronary event. 120 people, diabetic patients out of total 400 guys. At the same time, 100 diabetics out of 300 who had not taken ACE inhibitors. 100 out of. So the total, that is what he's given you. The total number of people, 300 guys who have not taken ACE inhibitors, out of which 100 developed an acute coronary event. All right. Now, what is he asking you? Relative risk, is it not? So what is relative risk? It's given by the formula A by A plus B, is it not? A by A plus B divided by C by C plus D. Okay? So what is A plus B here? Is it not 400? And what is C plus D? Is it not 300? So even without putting your pen down onto the paper, you can just go on, imagine the table and say that 120 divided by 400 divided by 100 divided by 300, which will be option E. Option E. So every time a question is given, what my intention for you people with this question is, don't try to make out the whole table. Don't try and put efforts into, completing the table. Always keep in mind to read the last part of the question, because from the beginning, he's going to give you all that nonsense you really don't want to have. Okay. The thing is, the last part of the question, that is critically important. Okay, you have to read that. You have to know what he is asking and trying to solve only that part. All right. So, is this clear to all of you? Everybody? Okay. Shall we proceed on to the next one? Awesome. Okay, the next question. Can you guys see the question? A new test to diagnose urinary tract infection in women is being evaluated. The comparison gold standard is positive urine dipstick plus urine culture. Results of the study are given below. Positive urine dipstick and culture, negative urine dipstick and culture. And he has given you the values, test positive, test negative. What's the new test's specificity? The time starts now. Okay, specificity, you weren't there for the last class. Okay, I'll discuss this with you. Okay, I got one response from Vidhatri. We talked about specificity yesterday, didn't we? Specificity, it deals with all those healthy people. It's the rate of healthy people. It's the true negative rate. Right, right. More responses, yeah. Good. Nice. 3 people responding now. And I think the time's up. Yeah, the time's up. Okay. Now from this question, what he's asking, he's only asking you the specificity. So from the table, from this table, what is that you require in order to calculate specificity? It's just this column that you need. You don't need any other information basically. So it's true negatives divided by all those people who are healthy. Is that right? So it's going to be 180 divided by 180 plus 20, which is 180 divided by 200, which is 90%. I can tell you with 99% confidence that you won't get this question on the exam. These are not the questions that are tested on step 1. Trust me. This is just to build a kind of confidence that your world is giving to you. Trust me, you won't have a single question of this sort. Rather, I'll give you some other questions and we'll try to orient ourselves towards exam-based questions, okay? Let's spare a moment for a couple of questions, then we'll chip in back. We'll deal with confidence intervals and central tendencies and all that, and then moment, please. Everybody can see? Can you see? Okay. So I'll read the question for you. A new blood test to detect prostate cancer is evaluated in 300 male volunteers. A needle biopsy of the prostate gland is done on all men with serum prostate-specific antigen concentrations greater than 5 nanogram per ml. 100 men undergo biopsy procedures, and 90 of them are found to have prostate cancer, and 5 are found to have chronic prostatitis. Which of the following is necessary to calculate the sensitivity of this test? The options are number of men with test results greater than 5 nanogram per ml and a normal biopsy specimen, incidence of chronic prostatitis in the general population, prevalence of chronic prostatitis in the general population, prostate biopsies of men with test results equal to or less than 5 nanograms per ml. Do this. I got one response. Okay, I'll just deal with this one question on the board. I hope that will not be a problem. I'll just deal with this one question on the board. All right. So what is it giving us? It's saying that there are 300 male volunteers. Altogether, we have 300 guys. See it on the board. Okay. So altogether, there are 300 guys. And it's saying a needle biopsy of the prostate gland is done in all men with serum prostate antigen concentration greater than 5 nanogram. So why do we have to do this PSA test? So people with prostate cancer have elevated levels of prostate-specific antigen. Okay, so a value greater than 5 nanogram per ml is diagnostic of prostate cancer. I mean, it's not confirmatory, but it gives you an idea that probably the patient has prostate cancer. Right? So that is what he's trying to evaluate. So PSA greater than 5 nanogram per ml. Okay, how many guys? Saying 90 of them because prostate cancer. There's prostate cancer. And here is no prostate cancer. Remember this? No prostate cancer. Okay. People greater than 5 nanogram, how many? 90. And what else did he say? He's given 5 with chronic prostatitis. But it doesn't matter actually because we are dealing with prostate cancer and no prostate cancer. Whether he has chronic prostatitis, whether there is benign prostatic hyperplasia, it doesn't matter. It's just a distractor. The thing that is given you that 5 people are found to have chronic prostatitis is a distractor. You have to think that if there are 90 guys, 10 guys will have prostate cancer. Okay, so leave that aside. Even that is not important. You read the last part of the question. Which of the following is necessary to calculate the sensitivity of the test? So all that you need to have in sensitivity is this column. So you need to find out what this is in order to find what the sensitivity is. So how do you get that? All that you need is all those people who have okay. So option A, number of men with test results greater than 5 nanogram per ml and a normal biopsy specimen. We already have this. So option A is wrong. Option B, incidence of chronic prostatitis. I mean, it doesn't matter if he has chronic prostatitis, benign prostatitis. So just rule out option B and option C. So you'll be left with option D. Everybody understood that? You want me to repeat? Everybody got this? Yes. Okay. Next question. Next question. A test with a known sensitivity of 98% and specificity of 99% for the detection of a given disease is performed on a population of 10,000 patients, of whom 0.1% of whom have the disease.
But my name is there on the thing.
Excuse me?
You can add students. Separate features. Whether he is taking for only one week.
I beg your pardon? Could you please text?
ऐसा करे तो कितना है बहुत cheap है ना तो $15 होगा तो क्या वो क्या होता है हाँ अभी शेयरिंग इससे मैं बात करना है मेरा उसमें ना गेस्ट का अच्छा कभी भी रन करना पैसे बहुत कम है ना I'll be teaching for 8
Okay. So he's given us sensitivity as 98%, specificity is 99%. He's given us that the 10,000 people of which 0.1% are deceased. So deceased is this column, which is A plus C. So he's given 1.1% of 10,000, which is 10. 0.1% of 10,000 is 10. A plus C is 10. Okay? And he's also given the sensitivity, that is A by A plus C is equal to 98%. Okay? So, substituting, what do you get? A. So, A plus C is 10. So, A is equal to 98 divided by 100 to 10. So, that's going to be 9.8. So, A is 9.8. A is 9.8. C is going to be what? 0.2. 10 people, 9.8, 0.2. No? Okay, I'll tell this again. What he's given us here is the A, B, C, and D, sensitivity of 98%, specificity of 99%. Okay, 0.1% of the population, which is 10,000, have the disease. So if 0.1% of 10,000 have the disease, this column altogether will constitute for 0.1% of 10,000, which is 10. So if the whole column constitutes for 10, what is 98% of 10? 98% of 10 is 9.8, which is 8. Okay, and this is 0.2. Okay, so far. Okay, so what's going to be B and D? What's going to be B and D? So if there are 10 people who are deceased out of 10,000 population, then who are all the healthy guys? 10,000 minus 10? So this is going to be 9,990. Is that okay?
B plus D. Just D.
Oh, okay. It's going to be B plus D. B plus D is going to be 9,990. Okay. So he's also given the specificity is 99%. That is B by B plus D is 99%. B plus D is 9,990. So what's going to be B? B will be 99% of B will be 99% of 9,990. Okay, so 99% of 9,990, what is that? 99% of 9,000. It's somewhere 9,000. Okay. Does somebody calculate like 9,890 is what? D. Right? So if this column is 9,890, it's what? 100. Okay? So now, if a person in this population receives a positive test result, which of the following is the probability that they actually have the disease? We talked about positive predictive value and negative predictive value yesterday. So how sure are you that if my test result is positive, I'm likely to have a disease is what is told by positive predictive value. Okay? You didn't get it? Okay, all right. So the question here is, which of the following is a probability that they actually have the disease in question? So we've done this test on them. So he's asking us a post-test probability. In spite of the test coming positive, how likely is he to have the disease? Now, if the positive predictive value, that means to predict that if a test is positive, the person has the disease. The test came positive, and also the person has the disease for sure. That is what is told by positive predictive value. For suppose if, let's say, the positive predictive value of a test is like, say, 50%. So in spite that the test came positive, you're only 50% sure that the person might really have the disease. So it's a poor test. It's actually not giving you the right information that the test result and the disease are in sync. Okay, so the question what he's asking you here is, you again? You guys are able to hear, right? So the question here is, what is the probability that they actually have the disease? The term actually is actually, it's giving you an information, it's giving you the direction to think in terms of positive predictive value. So how do you calculate positive predictive value out of this? So among all those people who tested positive, how many actually had the disease? Is that not what he's asking? Which of the following is the probability that they actually have the disease? So they should be having the disease, and they should also be positive. Okay, so that is A by. So the positive predictive value is A by A plus B, which is 9.8 divided by 100. Excuse me?
Yeah, 9.8, but yes.
Plus 9.8. Okay, 9.8 by. So that will amount to 9.8 divided by approximately 109. Okay. So that roughly will correspond to 8.9%, which is option A. Got this question? Everybody? Everybody online? Do you want me to repeat this question? You got the answer? Right, 8.9, Aditya. Right, you're right. Okay. One more question? Okay. This is a simple one. I expect all of you to answer this. An investigator is studying the impact seatbelts have on the severity of injuries incurred during a motor vehicle accident. Which of the following study designs would be most appropriate for answering the question? Answers? Yes, it's case control study because he wanted to evaluate the impact seatbelts have on the severity of injuries occurred during a motor vehicle accident. What he should be doing is just go to a hospital, pick up all the records from RTA files, okay, and see those people. Gather information from people who had seatbelts on and people who didn't have seatbelts on. So what is this like? He's going back in time and collecting all that information from the hospital records. All right. So he's going back in time, so it's a case control study. Okay? Right. Any question? You can interrupt me anytime if you feel like other options are like pretty close or something like that. Okay. Now this question. Well, before this question is answered, we'll talk about it a little. Okay? We'll talk about precision, consistency, and reliability, and accuracy and validity. Okay? So now you have a test in your hand, and you want to know like how important that test can be in order to evaluate a disease. So what are the qualities that you would want in that test to be? So it should be precise. Precise or consistency or reliability, they are all the same. Okay, they are all the same, the synonyms. Now, when you say that a test is precise, now say for example, you're the attending physician in a hospital, you're at your night rounds, all right? So there's this patient who's come and you want to know what his serum electrolytes are. Okay, you draw some blood, send it for serum chemistry. So now he says that the lab report comes with the potassium level to be 3.5 milliequivalents per liter. Okay, so you think that it's equivocal. I mean, you're not sure, like it's borderline for hypokalemia because the normal range for potassium level will be 3.5 to 5.5 milliequivalents per liter. So 3.5. What you do is you again draw a sample, give it to the lab, and again you get the result to be around 4 milliequivalents per liter. You do a third time just to be sure. Okay, so this time you get around 3.8 milliequivalents per liter. So the number of times that you are repeating the test, you're getting almost the same value within the normal range. So that implies that the test that has been performed in the lab is pretty precise. I mean, it's giving you the same value over and over again. So that is precision. So hitting the same value or hitting the same result from the test over and over, multiple number of times, that is precision. That is consistency, like when we talk about Virat Kohli, say, for example. So he's consistent in his batting. I mean, he scores all the time. So that is his precision, his consistency. And it's the same, like if a test is so precise, we can rely on that. You don't have to do a confirmatory test, all right? So if you get the same result over and over again, the test is reliable, okay? So that is precision, reliability, and consistency. Now what is accuracy and validity? Now say, for example, if the same guy and the same procedure that I just told you, now all the time, this time he got around 2.5 to 3. 3 times he was repeated the test and he got 2.5, 2.7, and 3. Okay, but actually the patient has no signs and symptoms of hypokalemia. It's pretty normal. Okay, so this time what is, there is precision in this particular test because over and over is giving you the same result. It's precise, but it's not accurate because since he has no signs and symptoms of hypokalemia, it's not an accurate test. It's giving you a false value, but it's precise. So a test can be precise, but not accurate. A test can also be accurate, but not precise. A test can be both accurate and precise as well. So we want to have a test which is both accurate and precise. Okay, so that's regarding precision and accuracy. And we'll talk about the bias at the end of the section. And we'll move on to a very, very, very important topic, central tendencies. I mean, I can't really emphasize how much important this part of the section of biostatistics is. It's really important. I want you, even if you want to have a 1 or 2 minute break, just take the break and we'll start with a fresh mind. We'll take a 2-minute ticker, okay? 2 minutes break time. Any questions? Anything that you want me to repeat again from yesterday's class? Because yesterday we have had that, the technical glitches very often that we could not actually concentrate much on the subject. So if there's anything, like Aditya told me to explain ROC, and I'll do that at the end of the section.
Are we doing bias today?
No. Probably at the end of the day. I mean, end of the section, because I put one reserve day because we kind of wasted a little time yesterday. So the easier topics, I'm pushing them back towards the end. Okay, let's get started. You're saying my 2-minute time is not over yet. Everybody ready? Okay. You'll have an idea about mean, median, mode. So mean is the average. I mean, it's the arithmetic mean. You just simply add all the numbers, divide by the number of values you're adding, right? That is mean. Median is the central tendency. Okay, if you have, like, say, I'll give you a few values: 4, 3, 2, 0, 1, 4, 5. So these are the values. What you do for the median is you arrange them either in the ascending order or in the descending order. Okay, you either arrange them in ascending order and descending order, and then you pick the middlemost one. If it's an odd number, it's easy to pick. If it's an even number, you take the middle two numbers and you find the average. Okay, that is median. You all must be knowing. I'm just skipping it a little faster. Mean, median, and mode. Mode is the most commonly repeated value. If, say, suppose 4, 4, 1, 2, 5, 4, 1, 3, 2, 1, 4, 6, 4, 4, 4. So among all these values, the most repeated one is 4. So 4 will be the mode. Okay. Now this is not as important, but the next thing that I'm going to talk about is more important. We'll talk about normal distribution. So anything that you're evaluating most commonly follow this trend. This is the Gaussian curve or the bell-shaped curve. So you're performing a test. You're performing some research. Maybe you want to find out what's the average blood pressure among individuals who are residing in a particular state. Okay, or you want to find out what's the average blood glucose levels, okay, among all the healthy people. Okay, so in all these things, they follow this normal distribution curve. Okay, this is called the Gaussian curve or the bell-shaped curve. Okay, so here, the centralmost one, the middlemost one, will be the mean, will be the median, and will be the mode. Why it is mode? Because this value is what is most commonly repeated. Now, we'll take an analogy. Let's say there's a class of 100 and you've given a test, okay, and you got the results back. Okay, on a scale of 0 to 100, you're evaluating what is the mean, what is the median, what is the mode. Okay, on an average, let's say this is 50%. This is 15 marks. Okay, this is the number of students. So most of the students, you found that they've got, on an average, 50 marks. More, that is, most of the students got somewhere around 50, like 40 to 60, somewhere around there. Okay, median is again the same thing. You're arranging them all in ascending or descending order and then finding the mean. Okay, so this is not important. The thing that you have to remember is standard deviations. So we're moving on to a new topic called standard deviations. Now, you have this class of 100. Each individual have got some variable marks. Some have got 5 marks, 10 marks, 35 marks. Okay, some got 75, 95, 99 marks. Some may even have got 100 marks. Okay. Now you want to know how much each individual's marks are deviating from the class's mean. The class's mean is 50 marks. Okay. Class's mean is 50 marks. And now say there's a guy, Raju. He got 35 marks. Now how much far away is he from the mean? He got 35 marks, he's here. So he's what? 15 marks away from the class's mean? Okay? Now there's another guy who got like, say, 70 marks. How far away is he from the class's mean? It's 20. So what we're saying is, his deviation is 15, his deviation is 20. Okay? So each individual's deviations are calculated in that manner. Now we want to know what is the average deviation of the whole class. On an average, how much are they deviating? Okay. Now how are we going to calculate this? So I'll give you this formula. It looks complicated, but it's not. I'll explain why. Now, X bar is the mean of the class. Now, X bar is 50. X is individual's marks. Okay, say X1 is 35, like in this case. X2, second person, is 20. X3 maybe some 40. Okay, and so on for 100 people. Okay. Now we want to know how much, on an average, each student is deviating from the class's mean. Okay. So what we're doing is subtracting the individual's marks from the mean. That is how you find out how much he is deviating, right? So this guy has got 35. The mean of the class is 50. So how much is the deviation? 35 minus 50, which is minus 15. We don't want to have this negative symbol in front because it's going to distort the results. Because symbol is, I mean, it's just like, it's not going to give you much information, okay? So how do we get rid of this symbol? What we're doing is, we'll square it. We'll square all these individual things. If I square it, it becomes what? Plus 225, right? So that way, we are eliminating this symbol. In order to eliminate this minus symbol, we're squaring it. Since we're squaring it, we also need to have that, that cancellation. So for that, we have to square. Okay? Divide by the total class minus 1. Now, why this minus 1 becomes important? If the size of the class is enormous, like say 10,000 or a million, you don't have to use minus 1 as well. You can simply put down the number, calculate, get it done. If the class size is small, 10, 15, or 100, then you do n minus 1. So this is standard deviation. Okay? Now, what is variance? What is variance? The same class. Now we have standard deviation is equal to sigma x minus x bar whole square divided by n minus 1. So how much is an individual variant from the class's mean? It's just another way of telling standard deviation. Variance is standard deviation whole square. That is, you just remove the square root. It's going to be x minus x bar whole square by n minus 1. It's not important, I'm just telling you. You won't get anything out of this. Okay, this is variance. So we've talked about normal distribution, then we've talked about standard deviation. Now, this is the graph, this is the mean. Now, standard deviation, there are some fixed values. Okay, you have to remember, you have to memorize this. One standard deviation accounts for approximately, anybody? Absolutely. 68%. Two standard deviations, approximately 95.5%. Three standard deviations cover approximately 99.7%. So what exactly is this numbers? So one standard deviation from the mean, is it less, is it more, right? That is standard deviation. So one standard deviation is from the mean plus 34% minus 34%. That will contribute to what? 68%. Okay? So people, if I say, how many people fall under one standard deviation in that class? So there are 68 people who will fall within one standard deviation. So their marks will fall somewhere between this point and this point. Okay? So it's going to be what? 34, 68. So you have at least 68% of the class will fall between the marks 34 and 68. That is information that you can give. What if I say how many people fall under two standard deviations? So there are 99.5% of the class will fall under this two standard deviations. Okay. So 2.5, 2.5. So what you can say from this information is there are just 2.5 guys who have scored more than 95. And there are 2.5 guys who have scored less than 2.5 marks, if there are any. Okay? Once again. So standard deviation, it will tell you the class intervals, okay? So 95%, if I'm talking about two standard deviations, it covers 95.5%. Okay, 95.5%. Since we have the mean of 50 marks, okay, 95.5%, two standard deviations. So there are at least 95.5 people, okay, who fall within the marks from 2.5 to 97.5. Good. Right. 97.5. Okay? Everybody's following? Responses? Everybody's following, right? Right, cool. Now, if it's three standard deviations, it approximates 99.7%. Now, we don't want this 0.5%, 0.7%. It looks odd, actually, in calculations and everything. So what we're doing is we're just slightly adjusting this two standard deviations and three standard deviations. So rather, instead of saying two standard deviations account for 95.5%, what I would say is 1.96 standard deviations account for 95%. Okay, you can still use two standard because it's almost close. So when you're calculating, you can still use two standard deviations. That's not a problem. Similarly, 99% will be accountable for 2.58 standard deviations. Okay? Okay. Now we've talked about normal distribution, then we've talked about standard deviation, variance, and then we've talked. And now let me talk to you a little about confidence intervals. What is confidence interval? What is a p-value? And what is the significance of a p-value? Why do you need to know this? Okay. So far we've talked about a class like who's 100 in size. So it's easy for you to take the values of 100 people, measure it, find what the mean is and what standard deviation is. Now, what if I say that I want to measure the mean of a whole school, which constitutes for like 5,000 people? It'll be hard for me to, in order to, go ask the marks of all those 5,000 guys and try to find mean. It's like a tedious process. I don't want to go through all that. So what I do is, I want to make this class as a representative of the entire institution. Okay, so this sample that I'm taking, if that is representative of the whole population that is under study, whatever I'm talking about this class will automatically be more or less representing the whole of the institution. In other words, if I say I want to know what is the average blood glucose level in a population, say in India, I can go out drawing blood of all those people, 125 million people. I'm not doing that. Rather, I would take such a kind of population that can be representative of the whole population of India. So what would be my sample? I'm not going to choose African Americans or Native Americans or North Europeans or anybody else, because the sample should be representative of the population under study. So what I'm going to do is, I'm going to pick up randomly some people, a small population from within India who are age-controlled match, or sex-controlled match, who are like with other morbidity and other comorbidities. I'll take that into consideration and then try and find out what is the average blood glucose level in the population in India. Okay, and then I'll project this information towards knowing the average blood glucose of the whole of India. Okay, so how am I going to do that? How can I be so sure that the average blood glucose that I calculate from this small section, from a small group of people, how can I stay so sure that the mean of this people is also the mean of the population? There should be some measure of, some statistical formula so that I can project my information onto the whole of the population. So I'm going to do that with mass intervals. Instead of saying that the mean of the class, which is 50 marks, is also the mean of the institution, constituting 5,000 people, what I would say is the mean of the class might lie in a certain interval which is representative of the population. I am making a hypothesis that the mean of the class, now this should be representing the whole of the institution, right? So what the mean that I got, now in order to say that it's the same mean of the institution, I can't be sure that it's the same mean. I mean, there are so many other people. So what I would say is, rather, instead of saying one single value, I'm showing all my intelligence here. I'm just saying that probably the mean of the whole institution might lie somewhere from this value to this value. It can lie somewhere between this. That is a confidence interval. Okay? Now, how confident are you that this mean should lie in these two values? I would say I'm a 68% confident. Or I would say I'm a 95% confident. Or I would say that I'm a 99% confident. Okay? The same information that we derived, one standard deviation, 68%, two standard deviation, 95%, roughly three standard deviation, 99%. I'm making use here. Okay? So when I say the confidence interval is 95%, I'm indirectly saying you that I'm 95% sure that the mean that I derived from the small population is representative of the whole of the population, that is the institution, and it should be lying somewhere between this value and this value. And if I say I'm a 99% sure, then it's going to extend furthermore, and it's going to the confidence interval is going to increase much. So when I say I'm a 95% confident, what information does the rest of the 5% give? I'm saying that I'm only 95% confident that this value, this mean, is lying between these two values. So there's a 5% chance that this mean might not be within these, and it can lie somewhere here or here. So there is 5% chance, by chance. I mean, I'm not confident about it. It can happen. If I randomly do the same test 100 times, I'm 95% sure that the average of whole of the institution should fall between these two values. But just in case, 5 times, it might be likely that the mean might lie outside this or outside this. Now, this 5% that I'm talking about is nothing but the p-value. When I say a p-value of 5%, p-value of 5% is what? 0.05, right? P-value of 5% is what? 0.05. This is what I'm setting for a test. When I'm giving a report in, say, Lancet or NEJM, New England Journal of Medicine, okay, if I'm saying that I've done this study and this is what my interpretation is, then you have to tell them like how sure you are. So then what he'll do is, if this is the paper, right on the top of that, he'll write p less than 0.25. So he's implicating that by saying p is equal to 0.05, he is actually giving that the information that is in the paper, he is 95% sure about. And that is 95% sure, representing the whole of the population on the study. Okay. Now again, how do you calculate the class interval? How do you calculate class interval? Any questions so far? You guys been following me? Anything that you want me to repeat? Because this is critically important, and I want to make sure everybody gets into this. Okay. People who are online, do you want me to repeat anything, any part of it? You're into this, you're getting along with this? Okay. So, how to calculate class interval? Class interval is given with the formula mean plus or minus standard error of the mean multiplied by z-value. No, it's not alien actually. Seriously, it's not alien. You know all of this. It's just a change in terminology slightly. Okay. So what is standard error of mean? It's in a way similar to standard deviation. Just that standard deviation is what we calculated among the small group of people, those 100 guys. Okay? So we calculate the standard deviation from those 100 guys. Now, the deviation could be a little variant if you're calculating it for the whole of the population. So how much is it variant from in the whole of the population from the original mean? Okay, that is given with the formula. Standard error of mean is equal to standard deviation divided by square root of n. N is the population size. N is the population size. N is population size. Okay. Now, if you're increasing the sample, if n value is increasing, what's happening to standard error of mean? Absolutely. And how do we interpret that? You're taking a sample that is actually representative of the whole of the population. Now, if you're taking a larger sample, if I'm to take the blood glucose levels of the whole of South India, I mean, I'm moving closer towards the whole of the population. Instead of taking, the population of Andhra Pradesh, which is a smaller sample, now I'm taking the population as a whole of the South India. So that is more representative or less representative of the whole of India. It's more representative. So the more you move towards the population and the study, the error shrinks down. You won't find errors. You'll find, you'll actually get closer to the real value, is it not? You getting it? So if you increase the population size, you're more towards the actual value. So if you're increasing the sample size, you're decreasing the error. You're shrinking the error, you're moving closer towards getting the actual value. Okay? So standard error of mean is this. So this is how you calculate confidence interval. Confidence interval is given by the mean that you've calculated, x bar, plus or minus standard error of mean and z value. Z is again the same thing. Z, if you're taking 1z is 68%, 2z is what? 95.5%, and 3z is what? 99.7%. Okay? Now, if I say, I'm talking about a 95% confidence interval of a mean, what should be the z value? If I'm telling that I'm talking about a 95% confidence interval, what should be the z value? Unless you multiply standard error of mean with 2, putting the z value, because z value of 2 accounts for 95%. Z value of 3 account for 99.7%. So if I'm saying that I'm talking about a 95% confidence interval, then obviously you have to make it in your mind that you're talking about a z value equal to 2. And if I'm talking about a confidence interval of 99%, then it's a z value of 3. So if I want to measure a confidence interval with 99% confidence, then you have to take the mean, you have to take the standard error of the mean and multiply it. Then you'll get a 99% confidence interval. Then you'll get a value which will be usually a range from this value to this value.
Standard error of the mean, same as
No, it's slightly different. Standard error of the mean is given with the formula standard deviation divided by the square root of the population. So confidence interval, this thing, this thing. Now when I'm talking about a 95% confidence interval, automatically I'm talking about a p-value less than 0.05. So all these things, if there's one information given to you, you have to derive out of it. And you have to know what exactly is it talking about. If he's given you that I'm talking about a 95% confidence interval, automatically you have to know that he's talking about a z value of 2 and the p is less than 0.05. Okay? You'll better understand this if you go through a question. Now we'll do a question based on this. Okay? So far so good. What's the time? Okay. Yeah, before that, I'll just, yeah. This is a question for you. Which of the following percentages of test subjects would have blood pressure values lower than 2 standard deviations below the average value? Answers? 5, 2.5, okay. Answers, people online? Okay, with that, 3 has come up with an answer. Gopinath has also come up with an answer. Okay, all right. He's talking about blood pressure values lower than 2 standard deviations below the average value. This is the average value. Okay. This is the average value. Okay. Now, what he's asking is blood pressure values lower than 2 standard deviations. 2 standard deviations is what? 95. Okay, roughly 95%. Okay. So he's asking blood pressure values lower than 2 standard deviations. If this constitutes for 95%, this constitutes for 95%. The extremes together constitute 5%. If the extremes together constitute 5%, what he's asking is below 2 standard deviations, this is minus 2 standard deviations, this is plus 2 standard deviations, right? Because standard deviation plus or minus, right? This is minus 2 standard deviations from the mean, this is plus 2 standard deviations from the mean. So he's asking below 2 standard deviations, he's only asking this portion. He's only asking for this portion. If together they constitute 5%, how much does this constitute? 2.5%? Okay? Once again, he's saying that you need to find out how many people there are who have a blood pressure level below 2 standard deviations. So 2 standard deviations constitute 95%. From the mean, you go forwards and backwards and you cover 95%. So you're left out with 5% who fall on either sides of the extremes. So together this plus this is 5%. You're asking below 2 standard deviations. So it's going to be 200%. Had it been, tell me all those people who don't fall under 2 standard deviations, the answer would have been 5%. Okay? Right. A couple of more questions and we'll call it a day. Yeah. A cohort study is conducted to evaluate the effect of daily illicit drug use on the occurrence of sexually transmitted infections among sexually active teenagers. 500 teenagers are enrolled, out of which 250 report using drugs on a daily basis, and another 250 report that they do not. The teenagers are followed for 3 years. Based on the table below, which of the following is the most reasonable for the researchers to conclude about the association between daily drug use and sexually transmitted infections? I couldn't make it in the same slide with the options as well, so I'll flip to the options. If you all have read the question, you've understood it, right? So I'll flip to the options, and just in case you need, you want me to flip back to the question, just tell me. The options are: drug use is not associated with STIs among sexually active teenagers. This is one conclusion. The incidence of STI is 5%. The relative risk of STI among daily drug users compared to non-drug users is 2. The researchers cannot determine the relationship based on the study design or the risk of STI among daily drug users is 7.3%. I'll flip back to the question again. Flipping back to the answers. Is it stable? Okay. Just kind of make this habit of reading the question just once, because that's the amount of time that you can afford actually on the real exam. If you orient yourself right from the beginning, that's going to help you towards your end of the preparation. And make sure not to extend your time so much. It's only going to sink you. And right after this, we have just one last topic. I mean, hardly 5 minutes, and then we'll call it off. Okay, people have come up with answers. They say the option C is the right answer. The relative risk of STI among daily drug users compared to non-drug users is 2, which is absolutely correct. Now, let's discuss why are the other options wrong. So drug use is not associated with STI among sexually active teenagers? No, because we have the relative risk from this to be 2. So daily drug users are 2 times more likely to have STIs. Okay, so you can rule out saying that STI is not associated with sexually transmitted infections. Okay, so option A is wrong for that reason. Okay, the incidence of STI is the purpose that I put on this question is to make you aware of the fact that you can't calculate incidence with the 2x2 table. All that information that you can do is sensitivity, specificity, positive predictive value, negative predictive value, and prevalence. Prevalence is one more thing that you can derive out of it. I'll tell you why. Now, this is the table. These are the people with the disease. These are the people with no disease. This is the risk factor. This is no risk factor. All right. So we have all those people who are deceased, and we have the total population. Total population is what? All diseased plus non-diseased. Is that not? So these are the people who are healthy. These are the people with with the disease. So if you add up all those people with the disease and add up all those people without the disease, you get the total population. Is it not? So these are the people who are already having the disease. So disease divided by total population leads to what? Prevalence. But it does not tell you the information about new cases. These are the cases which are already existing. Incidence is what? Trying to find out new cases. So the new cases divided the people at risk, that will be incidence. So you can't calculate incidence with 2x2 table. All that information that you can derive out of a 2x2 table is you can calculate prevalence, sensitivity, specificity, and all the other things. Okay. So that is that. Yeah. Last question. Question for the day. It's kind of tricky. I want you to focus. Answers. Oh, there's one person who's come up with an answer, and she says B. Okay. It's B. Two people. Okay. Shall we move on to discussing the answer? Yes, you're all wrong. Congratulations. But that's not a problem. I mean, it's okay. It's always good to make mistakes. No. We'll discuss with the answer. The p-value given here is less than 0.005. Had it been a p-value less than 0.05, had it been p less than 0.05, then we could say confidence interval of 95%, z-value of 2. You can take all that. Since p-value is less than 0.005, which is actually less than 0.01 as well. P-value 0.005 is also less than 0.01. So what constitutes for p-value 0.01? What should be the confidence interval? What should be the z-value? If I'm telling p is less than 0.01, that is p is less than 1%, the confidence interval is what? 99%. If the confidence interval is 99%, what is the z-value? Is it not 3? 3? I told you for one, if the confidence interval is 99%, it's z equal to 3. If the confidence interval is 95%, z is equal to 2. If the confidence interval is 68%, z is equal to 1. Right? So, for p-value less than 0.005, which is less than 0.01, the confidence interval will be 99. And for the 99% confidence interval, you have to calculate with a z equal to 3. Okay? So, given the question, the mean plus standard error of the mean is what? 0.5 plus or minus 0.2. So, this is the mean, this is the standard error of the mean. So you've got to calculate 0.05 plus or minus 0.02 into what? 3. So what are you going to get the values as? 0.5 plus or minus 0.6. So what is 0.5 plus or minus 6? What is the confidence interval? 0.5 plus 0.6 will be plus 0.11. And 0.5 minus 0.6 will be minus 0.1. Okay? So now that we've got p-value which is less than 0. It's far more less than 0. So it actually is negating everything. So the given information is false. Or in another way to interpret it, what is a p-value of p-value less than 0.005 with a mean and standard error of 0.5 plus or minus 2 is only merely because of a chance, because of a random chance. Since the confidence interval is this, which is less than 0, so the confidence interval is less than 0, the original thing, that is p less than 0.005 of what is given, should have been false, or it's not falling into this category. It's falling somewhere, like if I draw the table again, so not the table, the graph. For this graph, for p-value less than 0.001, it's constituting 3 standard deviations. So he's falling somewhere here or here. So the result that is given is actually falsified. So the option would be, this difference would have arisen by chance alone. And how frequent is that chance? Like I said, I'm talking about a 95% confidence. I am saying that 95% I'm sure that this mean should fall within these values. And what does the rest of the 5% mean? The rest of the 5% mean that by chance, there can be a 5% chance that it might not fall within these values. That is what we're talking about, right? Here it's the same thing. Here it's the same thing. There is he's given what? A p-value less than 0.005. So this is the chance that it might fall away from what I'm showing. This is the chance that can happen randomly. This is a random chance for that question. So the random chance would be 5 divided by 1,000, which is 200. So 1 in 200 times, the values can fall outside of what we expect to be. Want me to repeat? Sure. So here, the trial to investigate the effect of a new drug on blood cholesterol, okay, refractory compared to conventional treatment, the mean plus or minus standard error is 0.5 plus or minus 0.2. Okay, so because we are getting a confidence interval which is less than 0, which indicates that the new drug or the new treatment available is no better than the existing one. That's the information you derive out of it. Since it's not falling within when you calculate with taking p less than 0.005, when you calculate what's the confidence interval you're getting it less minus 0.1 to plus 0.11. This is the confidence interval you're getting. Okay, so the confidence interval is less than 0 here. Like from 0 it's going to minus 1, is it not? So when a confidence interval is 0, what is it actually telling you? It's saying that the original treatment, the standard level of care, is far more better than the new care because it's including 0. 0 is like canceling out, right? No? Okay. I'll tell you one more time. I want everybody of you to read the question again. In a trial to investigate the effect of a new drug on blood cholesterol refractory compared to conventional treatment, the mean or standard deviation of error is 0.5 plus or minus 0.2. Okay. With a p-value of less than 0.005. When he's given us that the p-value is less than 0.005, he's telling us that the confidence interval is 99%. Because p is less than 0.005 implies p is also less than 0.01. 0.005 is less than 0.001. So it's 0.1. Is that not? Okay. So p value less than 0.01 is what? Confidence interval of 99%. Okay? So you want to have your 99% confidence interval somewhere above zero, at least above zero, and it can extend anywhere. Now, he's given 0.5 as the mean, plus or minus, what? 0.2 as a standard error of the mean. So what is the formula for confidence interval? Confidence interval is mean plus or minus standard error of the mean into z value. Since he's already given you the p-value, which is less than 0.005, which constitutes for 99% of the confidence interval. So a 99% confidence interval is what? Z is equal to 3. So when you calculate, you get 0.5 plus or minus 0.6. So that is equal to minus 0.1 to plus 0.11. This is the confidence interval you're getting. Now, since the confidence interval that you have calculated is less than 0, because in order to get minus 0.1, you have to cross below 0. So 0 to minus 0.1. So since it is falling below zero, the original thing that the new therapy is better than the older one is false. No?
Yes.
Still not getting it?
We got it.
Question?
How should the two have written?
Okay, I'll tell about it. So now we show that the question is wrong. So when it doesn't fall in this category, if the mean and standard when they calculated, now since we're getting an answer which is not predictive of confidence interval, so it's actually not falling in this 99% confidence interval. Okay, from this answer, what we understood is it's not falling under the 99% confidence interval. Okay, so if it's not falling in 99% confidence interval, it's outside of that. So it must have happened out of a chance alone. So how much is that chance? The chance is equal to t is equal to less than 0.005. This is the chance, random chance that all this has happened. This is a random chance. Okay, so if p is equal to 0.005, just doing the math, if it's 0.005, it's nothing but 5 divided by 1,000. If it's 5 divided by 1,000, 5 ones, 5 200s. So 1 in 200 times, there's a possibility that an event can occur randomly. There is 1 in a 200 possibility that this particular event can happen randomly. Okay, cool.
What about an exam? We won't have this much time to write it out loud.
Practice. I'm sure the question you've asked is a question so many people will be having. So the trick that you have to apply is don't keep solving for the question. Don't take in all that information that is given to you, because at least 60-70% of the information provided to you is all crap. Just look at the last part of the question, what he's asking, and try and search for the answer within the options. Okay, that's the best deal that you can do. Okay, everybody understood? Okay, the other questions maybe we'll do it sometime later. I think we've had enough of the class. Everybody's like totally tired. I have a few more interesting questions. Maybe we'll solve it sometime later. Just before you leave, a small thing I just want to do. If you guys can spare 5 minutes, or do you want me to tell tomorrow? No? Okay. Because we're already lacking. There's just this one topic. So 2 topics, and I can wind it up in 5. Sure. I'll send my PPT as well. Not a problem. Okay. So anything that you've got for me? Any questions? Anything? Because we actually, all these sections should have been completed yesterday. Because of all that mishap that has happened yesterday, we couldn't do it. But I'm sure we can enjoy it from tomorrow onwards because we're going to start psychology and psychiatry, and so we'll have a lot of fun from tomorrow. We'll talk about more movies which you like. We'll talk about characters and picturizations, and hopefully we'll try to make as much interesting as possible. I'm afraid that we can't complete the whole schedule within the 6 days, now that we are lacking by 1 day. We'll plan about it anyhow, okay? It was good to meet you all. Thank you so much. Have a great day. And Aditya, I will send you all that presentations that you want at the end of this thing. I mean, on the last day probably, I'll tell you. Okay. And yeah, you asked me for ROC. Okay, are you gonna hang around here? I'll talk about ROC. When people who want to leave, they can talk about ROC with you. So 1 minus specificity, and there is sensitivity. Okay. Now, ROC, which is receiver operating curve, is basically done for a test. Okay, what kind of test do we need to employ in order to have the best result? What kind of test do we need or do we want? Like, do we want a test which is highest sensitivity or which is highest specificity? It depends upon the requirement we have, right? So that is shown in this graph, okay? So we want a test which has got high sensitivity. High sensitivity is here, right? So if the test has a graph which is parallel to the x-axis on the highest mark on y-axis, that test will have the highest sensitivity. So we want to employ this kind of test in order to find out all the rare diseases, right? So we want to pick all those, tiny little cases that we might have missed on other tests. So we want to have a 100% sensitive test so that we can find out all those people who have the disease, especially these rare kind of diseases, right? So we want to employ a test which is high sensitivity. So on the graph, which of these graphs have the highest sensitivity? So highest sensitivity is this graph. So we also want to make sure that we have lowest false positives. So 1 minus specificity is what? Since specificity is given by the formula. This is the 2 by 2 table. A, B, C, D. Is it not? D by B plus D. So specificity is D by B plus D, right? So what happens to 1 minus specificity? Subtract D by B plus D, which will be, if you do the math, D and D get cancelled, you get B by B plus D. Okay? So what is B by B plus D? Blurred. Are you able to see?
Yeah, he said yes. He said yes.
Okay. Okay. So we got 1 minus specificity is equal to B by B plus D. From the table, B by B plus D is what? These are true positives, these are false positives, these are false negatives, and these are true negatives, right? So B by B plus D is what? False positive rate. False positive rate. Is that okay? Right. So on the graph, we want to have such a test which has got highest sensitivity and 1- specificity or false positive rate, right? So we want to employ tests which has high sensitivity and lowest false positive rate as well. Although they don't correspond, okay, don't get fooled by this thing. I mean, as sensitivity is increasing, the false positive, no. These are independent variables which are plotted on the x and y axis. You want to have both things. You want to have high sensitivity. You want to have low false positive rate. So the test, which will be corresponding to this, will have high sensitivity and low false positive rate. I hope you got that clear. Did you?
Yes, sir. Yes, sir.
Cool. Anything else you want to
Thank
add?
you.
Yeah. Pleasure, Roman. Yeah.
Sir, what about last part, that plateau?
Excuse me?
What about the plateau part of the graph?
In this graph?
Yeah, yeah.
Yeah, the plateau is actually telling you that it has, higher sensitivity.
Okay, so this graph only shows the highest sensitivity, right, sir?
Yeah, absolutely.
Oh.
Actually, this is not important as per if you're following Kaplan's, I would not recommend it for biostatistics and behavioral, because there's too much stuff in that. I mean, you'll get lost talking about all, there's so much in that. It's actually not important. Don't waste your time following Kaplan for behavior. You have 100 cases of Conrad Fisher, you have UWorld, you have first state. I think that's a big deal. I mean, that's fine. You don't want to have to go through Kaplan and try to memorize all that stuff. It's not really important.
Sir, what would be the approach? I mean, I need to study the questions and form a way to solve that questions like that, or
well, it works out differently for different people, Aditya. Like, if you'd ask me, I would say, I mean, the way I did was I used to read the whole of the question, then concentrate on what he's asking, and then go through the options. There's a friend of mine who used to read the last part of the question initially, and then go back, I mean, have a look at the options, and then go back to the question. So I would just say do the things which you feel are best for you. I mean, when you're practicing, like when you're doing UWorld, trying to do one block, okay, using one method, and trying to do another block with another method, and trying to see, I mean, just compare yourself. I mean, how you're doing better, where you're doing better, and you just stick on to that. That should do.
okay. Is it possible to do a pre-exam rehearsal? Like, I mean, I can form all the concepts in a single way and utilize them later on when the question comes. So it is.
I beg your pardon?
Yeah. What I mean to say is, I need to form the ways how to get up to the answer before the exam.
Okay.
So is it possible to form in Biostats?
Yeah, what you do is when you're reading through the question, just highlight it, the most important things that you think are important for the question. Okay, just when you're reading the question, just highlight with the mark. You guys have lunch here. Okay. Just highlight it the most important things on the question. Okay, and go through it. And when you're looking at the options, just have it at the back of your mind. I mean, what you've done. Just in case you don't understand the question also, just by looking at the highlighted parts, you can actually have formative, like, okay, what he's trying to ask. And that, trust me, it will come only and only through practice. The more the number of questions you do, the better you get. So UWorld is giving you like what, 2,500 questions, but don't neglect NBMEs. Altogether, if you do from NBME 1 to NBME 18, they constitute around like what, 2,800 questions. That itself is forming your question bank, to be frank, right?
Yes,
so, yeah, don't miss out on any NBME. Do them like practice. Learn from them as well, I would say.
Yes, sir. I want to say the same, that if suppose there are 5 questions on the same topic, we can form a note which will give the answer of the all question. You know what I mean to say? Yeah.
You want me to do that?
No. Okay. Is it better way or not? I just want to ask you.
I would say it would be time consuming actually. If anybody would ask me, I would say keep it simple, keep it crisp. I mean, target like 6 months, 8 months, whatever your study time is, and trying to make sure that you finish in that period. Because once you cross that, there'll be a kind of slack actually. I mean, you won't feel that interest in doing questions, and there's this really, you become sloppy and slotty, and you don't want that to happen to you. So just fix a time period, get it done in that, move away. So
the better thing is be simple, right?
Be simple, yeah. Even if you have resources and if you can use your computer well, I would not even recommend annotating all that UL stuff onto this first tape, because it really consumes a lot of. I'm telling it out of my personal experience. It really consumes a lot of time. And if you can just like take a video like that, I mean, MacBook has that option. I don't know, like others do or not. Just take a video or a snapshot or a picture out of it and then read from that. If you can do that. Now, if it's hard for you, then it's better to annotate. Like whichever is comfortable with you. Just don't try to, trouble yourself. Don't trouble yourself.
Yes, sir, I'm getting your point. Yeah, that's true. I think it's better way. Yes. Thank you.
Yep. Cheers. Okay. I'll take leave. Bye. Yeah, sure. Please have a seat.
You told us that you recently wrote your
Excuse me? Yeah.
and you did really well.
Not